Hey all, welcome to lesson 5.5. In this lesson we'll go over the equations for power. Now in general, power can be thought of as a powerful person or a powerful country is someone that can do a lot of work in a very short amount of time. That is exactly what power is in physics. It's the ability of something to do work quickly. We'll have a more mathy definition, but that's the basic idea. They get a lot done in a short amount of time. Our definition is the rate at which work is done. The rate at which work is done. That's our definition for power. There's going to be 3 equations total for this, but we'll start out with 2. Off to the left here, I'll have that rate-based equation, work divided by time. Anything that is a rate will have time on bottom, and the other equation takes the same form, except it'll be change in energy over time. Labeling the units, this is of course power. The unit is going to be capital W, watts. Be very careful there. W stands for watts, it's the unit for power, but also W is the variable for work, so you need to be careful with those. T is time, which of course is measured in seconds. And like I said, this is still work, which is measured in joules. So P stands for power, it has a unit of watts. T stands for time, it has a unit of seconds. And work, W stands for work, has a unit of joules. Over here, you can see these equations kind of mirror one another. They show, once again, like we saw in a previous lesson, that work is a change in energy. In that previous lesson, we said that work is a change in kinetic energy, but here it's a little more general. So this is change in energy, which is measured in joules. Watt is the unit for power. You can see this on light bulbs. Light bulbs are anywhere from, 10 to 200 watts. 60 used to be the standard, but things are changing because of more environmentally friendly stuff. For large machinery like cars and air compressors, they might use something called horsepower. So horsepower is just a different unit of power. We're usually going to use W, but sometimes we'll use this, so I'll throw it in here anyway. This is a common unit of power. Used for automobiles and heavy machinery. It's a larger unit, so 1 horsepower is much more than 1 watt. In fact, it'll be 1 horsepower is 745.7 watts. You don't have to memorize this. Well, who am I kidding? This online semester, you don't have to memorize anything. But I don't expect you to memorize it. It's just worth noting. 1 horsepower is equal to 745.7 watts. So that's the basic story of power. We're going to look at one more equation before we see an example. And here it is. So this is technically not a separate equation. This is just one more way to write it. We'll do so with a derivation. So here's what we started with. Power is equal to work over time. If you recall from lesson 1, 5.1, work is equivalent to force times distance times cosine theta. I'm going to drop the cosine theta. So S is displacement, F is force. And we'll leave the time down there. What we see when we write it this way, when we replace work with force times displacement, which is what work means, this here will show up. Displacement divided by time, which we learned a long time ago, is velocity. Displacement over time is velocity. So we can rewrite that as velocity, which leads us to our other way to write power. So power can also equal force, which is in newtons, times, actually technically it's average velocity. That's what that line means above the top of it, measured in meters per second. So don't worry about that step. The important thing is to have this written down. Power equals force times average velocity. That's our third way to write the equation. So there's 3 ways to write it total. All right, on to an example. We'll try to use 2 of these 3 equations. First, we'll look at a car. All right. Here we go. Calculate the power in HP, horsepower, of a 1,200 kilogram car that starts from rest and reaches a velocity of 25 meters per second in a time of 4 seconds. Calculate the power of a 1,200 kilogram car that starts from rest and reaches a velocity of 25 meters per second in a time of 4 seconds. Breaking it down a little bit, of course we know that kilograms is a unit of mass, so I'll write an M there. If something starts from rest, that means that initial velocity is 0. You can write it off to the side or write it up here if you got space. I found some space there. VO equals 0. It reaches a velocity of 25. That must be the final velocity if the initial velocity is 0. And then T is 4. So there's 2 ways to look at this. We can actually use, I believe we can use either equation, but I'm going to jump to this one because there's something about velocity in there. We'll have to draw on some old knowledge in order to solve this, but it is actually quite easy to solve. Power is force times average velocity. Well, there's 2 old equations that we haven't seen in a while that will be used here. Force, Newton's second law says that force is mass times acceleration, so we can use ma here. Average velocity, you can calculate average velocity the same way you calculate the average of 2 test scores. you would take each test score, add them together, and divide by 2. Basically, to get average velocity, you get the initial plus the final and divide by 2. I actually did that divided by t for some reason. So that's m times a times v initial plus v final over 2. So we're a little closer. We have m, we have VO, and we have VF. We don't have the acceleration, but drawing from chapter 1 knowledge yet again, we know that acceleration is change in velocity over time. So here will be the last step, the final version of the equation we use. Power is equal to m times, acceleration is something else now, v final minus v initial over t, that's where I was writing t before, and average velocity is still just going to be VO plus VF over 2. So the nice thing is that those VOs are going to go away. They're going to be 0 because it starts at rest. You could write them in anyway if it doesn't throw you off. Me, I'm going to drop them. So power is m, which is 1200, times VF, which is 25, over t, which is 4, times VF, again 25, over 2. So power is going to be 93,750 watts. A lot went into that equation. I wouldn't expect you to pull those 3 equations out of nowhere. The point is, do you know how to use this equation? Could you plug in an average velocity of force in there? It's important to know your units as well. That's our standard unit. This problem asks us to get the answer in horsepower. So we'll do that as well. In order to get horsepower out of this, you'd multiply it by, I guess I can just show it off to the side. In order to cancel out watts, you would put watts on bottom, 745.7, and horsepower on top. Hold on, where did I get that? So I'm multiplying times 1 HP over 745.7. The reason I did that is because there's 1 horsepower for every 745.7 watts. And you put the W on bottom in order to cancel them out. They cancel, and you get an answer in horsepower, which will be 125.7. Usually your answer is going to be in watts, but I thought I'd demonstrate the difference between those. This is why they use horsepower instead of watts for cars, because 93,000 is a tough thing to conceptualize. We humans have an easier time talking about smaller numbers. It's easier to compare smaller numbers with cars. So powerful things are going to use these units. Most of the time in our class, we're going to use that anyway. So, crazy example, but somewhat interesting nonetheless. We'll take a look at one more, which is a little easier, a little more interesting, in my opinion. All right, let's go. Here we go. Calculate the work done by an elevator motor. I should say that again. Calculate the work done by an elevator motor, so the thing propelling the elevator upwards, that carries 800 kilograms up for a distance of 30 meters in a time of 14 seconds. I'll also add that it is a constant speed. Reading that again. Calculate the work done by an elevator motor that carries 800 kilograms up for a distance of 30 meters in a time of 14 seconds. Let's look at the two equations that we haven't used and see which one we like. So we have the time, that's great for us. Both of these have the time in them, so the decision is basically, do we want to expand W or do we want to expand the change in energy? I don't like the work definition. There's something very flimsy about this equation. Figuring out the angle and figuring out what type of force is present, what direction is S, what direction is F. So I prefer to try to avoid this. In doing so, I'll go over here. We'll find that it's actually technically the same equation, but our change in energy. We know that the kinetic energy is not changing. The kinetic energy remains constant because our velocity remains constant. So the only change here is our change in potential energy, which is given by mg delta h. Coincidentally, it's actually the same thing. The change in height for the elevator shaft is the displacement. There are just two different ways of saying that the elevator goes up 30 meters rather. The force here is gravity. Turns out that the potential energy equation has the gravitational force in it right there, mg. So technically they're the same equation in this context, but in my opinion, this one's just a little cleaner. A cleaner way to represent it. So let's rewrite it with this here. mgh is potential energy, but mg delta h is change in potential energy. And now we have a beautiful, perfect, solvable equation. We'll plug in the numbers from here. Power is 800 times 9.8 times 30 divided by 14. And so the final answer for this elevator shaft is 16800 watts. They did not tell us to calculate the power in horsepower, so we assume that they want the standard units. Watts are the standard units, horsepower is something special. So there's two examples on power, two different equations basically. We have the work over time equation, which is also technically change in energy over time, and we have the force times average velocity equation. These three equations can be found from one another, so really they're the same thing. There's just some convenience in writing them in different ways. So that's it for the power lesson. Go ahead and post your notes on Google Classroom, and if you have questions, let me know.